Hello everyone, welcome to my channel. We are going to solve mechanical metallurgy questions of GATE 2011. First question is the angle between the line vector and the buzzer vector for an edge dislocation is. Okay guys, so now if you see this edge dislocation, then this is somewhat like this. Okay, so this is the line. So this is your buzzer vector line that is denoted. This is the dislocation line denoted by T vector, and the buzzer vector is in this direction. Okay, and the angle between them is 90 degree. Okay guys, so the answer will be 90 degrees. Next, yeah, in fracture toughness characterized by K1C or J1C, 1 in the substrate indicates loading by, right guys, this is called as K1C. 1 is in the Roman. Okay, similarly J1C, this is called as 1C. Okay, so it is not KIC, basically it is K1C. Okay, so it is crack opening mode or forward shear mode or parallel shear mode or perpendicular shear mode. Okay, so this is your crack opening mode. Okay, so there are three different types of mode. Now if you see, I'm just drawing a sketch to understand this. This is just a sketch. Okay, now the first force is along this direction, which is denoted by your K1C. Okay, so this is your crack opening mode, because here it is a crack and this force is directly such that the crack got open. Okay, so that's why it is called as crack opening mode. Next, it is if you apply this force along this direction like this. Okay, so along this direction, along this width direction. Okay, this is your width, so along this width, then it is called as forward shear, and this is called as K2C. Okay, and the next application of force is like this. Let me draw. It is along this thickness direction. Suppose this is your thickness, right? So this is along your thickness. Okay, so this is called as parallel shear mode. Okay, and this is called as K3C. Okay, so these were the three different types of modes. Next, when load is applied to a material, instantaneous strain develops with, when we apply certain load, suppose this is your tensile 1, and if you apply certain load, right, so there is a strain development. So this strain develops with the speed of the light. This strain developed with the speed of the sound. Okay, so in this question number 22, the correct answer will be the speed of sound. Okay, next, for a given ductile material, which one of the following tensile properties obtained with non-standard specimen is not comparable to that obtained with standard specimen? Okay, So one is your standard specimen and one is your non-standard specimen, right? So I am just giving a brief idea like what is the size of the standard one. So there are various ASTM standard or international standard. So like ASTM E8, okay, or some ISO like 6092 part 1. I think it is 6092 only, but I will have to see. But so now it is a like ASTM E8, right? So now suppose this is a cylindrical sample, okay. So this gauge length L which is there, so L is equal to 5 times of your D naught. That is the dia for a cylindrical one, right? Now suppose this is not a cylindrical one, then length is calculated like it is 6.25 times root over your area, right? This is for a plate type or flat specimen, okay. Now this is the standard one, but suppose someone measures using a non-standard sample. Non-standard samples can be like this. Your length is suppose your 7 times of your D naught or something like that, okay. So what is the property which is not going to be comparable, right? So see here, elongation to fracture, tensile strength, uniform elongation and yield strength, right? Guys, see, tensile strength and the yield strength are material property, right? So if you try to measure with a standard or a non-standard, so these two properties will be always comparable, right? But if you see the elongation to fracture, now suppose this is a thin sample or a smaller gauge sample, right? So elongation to fracture means the total elongation before the fracture which is happening, right? So this is one length and this is another length, right? So the elongation to fracture will be different in both because the initial length which is taken is different, okay. So now if you see this graph, okay, so this elongation to fracture, this elongation, like here it may be 5 mm but here it may be 8 mm, okay. It is different, it will be different. So elongation to fracture can be the answer. Uniform elongation, uniform elongation means tells you the elongation up to your UTS, okay. See, this was for the fracture, sorry, this was for the fracture initially, okay, and up to here, up to this UTS point, this is called as uniform elongation. So similarly, the uniform elongation can also be different, okay. So that's why A and C both are the correct options, okay guys. So I think the marks were given to all for this question number 23. Okay, next. The largest size of immobilized segment of dislocation in a frank reed source contained in a polycrystalline material is of the order of grain size, okay. It is of the order of the grain size in a metal of 10 micrometer grain size, okay. So this is a problem of frank reed source, right? So frank reed source, suppose that this dislocation is been at two locations which are separated, so this separation is equal to the grain size, right? So now it is showing that in a metal of 10 micrometer grain size, the shear stress required to operate such frank reed source is 100 MPa. Okay, first condition. If the grain size in the same metal is reduced to 10 nanometer, the shear stress required to operate such frank reed source would be, right? So we know the formula. Tau is equal to GB by L, and this is your L, okay. So length, so tau is inversely proportional to the length of this dislocation. So length here it is defined in terms of the grain size, that is 10 micrometer in the first case. So tau in the initial case it is 100, right? So let it write 100 equal to G, and B you don't know because this let it be a constant, and L in the first case it is 10 micrometer, so 10 into 10 power minus 6 meter. Okay, in the next case we have to find the stress. So stress, let it be tau dash equal to GB, because G and B will be both constant and will be equal to the first condition, right? That will be equal GB by L. So here it will be L dash. So L, the next case it is 10 nanometer, so 10 into 10 to the power minus 9. So let us divide both. Okay, so it will be 100 by tau dash is equal to 1 by 10 into 10 power minus 6, and here it will be 10 into 10 power minus 9, so it will be 10 power minus 3. So tau dash will be 100 into 10 power 3, that means 10 power 5, and the answer will be in ampere. Okay everyone, so option C. Let us go. Which one of the following reactions in FCC or BCC crystal with lattice parameter A is energetically favorable? So this is, we have to predict whether this is energetically favorable or not. So that means all this reaction which is going to happen vectorially, it is going to be correct, but we have to see energetically whether this is correct or not, right? So to do that, first we'll have to write this complete equation. Okay, so if the reaction between these two will happen, then what will be the product? So it will be A by 2 1 bar 0 1. Here it will be A 1 1 0, right? In the case of B, it will be A 1 1 bar 1 1 bar 1 0. Here it will be option D, right? So it is A 1 1 1. Okay, so we know this all corresponds to your Berger vector, right? So to predict this one, so we need to have this condition, that is b1 square plus b2 square should be greater than b3 square. That means, so there will be decrease in the energy, right? Because energy is equal to half GB square, so E directly proportional to B square. Okay, so let us see in the first case first. Okay, so first case, b1 square plus b2 square will be a square by 4 into 2 plus a square by 4 into 2, and here transformation is taking place, so here it is a square by 4 to 2. So it is like a square by 2, so it is like a square to changing to a square by 2, right? So there is a decrease in energy, right? So this is going to be favorable, right? So from here we can directly say A is the answer, but let us check for other options also. Like A we have checked, let us check for C. So b1 square plus b2 square, let us write, so it will be a square by 4 into 3, a square of 4 into 3, and it is changing to 2a square, right? So it will be 3 by 4 plus 3 by 4, that means 6 by 4, that means 1.25 a square changing to 2a square. So here there is increase, so this reaction is not going to be feasible. Let us check for B. So a square by 4 into 2 plus a square by 4 into 2, it is changing to 2a square. So this implies a square is changing to 2a square. So this is also incorrect. Okay, let us see option D. A square by 4 into 3, a square by 4 into 3 is equal to 3a square. So here also 1.25 a square changing to 3a square. So this is also not correct. Okay guys. So guys, did you understand how I am writing this b1 square? Right. So now I will just tell you. I think many, if you don't know, like b1 here in the first case, suppose I am taking this one, it is equal to a by 2 1 bar 1 0, right? So if you take the modulus of this, so this modulus will be equal to modulus of b1 will be equal to, just I want to write this modulus of b, then it will be a by 2, and here it will be whatever it is, so that will be in a root form. So root 1 plus 1 plus 0. So a by 2 root over 2. So similarly we are finding this b square, so it will be a square of 4 into 2. Okay guys, so this is the method. Okay, let us proceed. Match the hardness test methods in group 1 with the indenter used in group 2. Okay, so first it is Brinell hardness, then Vickers hardness, Rockwell C hardness, Rockwell B hardness. Let us see a Braille indenter square base pyramid, diamond pyramid, 10 mm diameter steel ball, 1.6 mm diameter steel ball. So Braille indenter. So Braille indenter is used in Rockwell C RC value, right? RC is used in many applications. All automobile industries, all small scale industry use this RC, as well as the big industries also. And a square base diamond pyramid, it is used in Vickers hardness type. 10 mm diameter steel ball, so this is used in Brinell hardness. 1.6 mm diameter steel ball, it is used in Rockwell B. Okay, so Rockwell B has got this 1.6 mm diameter steel ball, right? So what is the option? 3 2 1 4. 3 2 1 4. So option B. Okay, let us proceed guys. Okay, so this is a question where there is a single statement which is useful for both questions. So shear modulus of copper is 45 GPa. Lattice parameter of copper is 3.61 ampere. Okay, the magnitude of the Berger vector in copper is, okay, so copper, it has got FCC, right? So what is the Berger vector line? So it will be along this 110, right? And this will be along this line. So the Berger vector value will be half of this line. Okay, so V vector is equal to A by 2 110, right? So 110, let me draw this so that you can understand better. Okay, so 1 okay, so direction will be like this, right? This is your slip plane. So one of this direction, suppose you can take this direction, or this direction. Okay, so this is a diagonal of the face. So diagonal of the face will be, here it is a, so it will be root 2a, right? Fine. So let us find this. So this diagonal will be root 2 into a. A is how much? That is parameter 3.61, and the half of this will be the value of this Berger vector. That is what it is over here. So a by 2 into root 2. So a by 2 into root 2, right? So this is equal to, I've done the calculation, it is 2.55 angstrom. So option A. Okay. The next question. The elastic strain energy per unit length of dislocation line in copper is. So elastic strain energy per unit length is equal to half of GB square. Right. So it will be half into G. G is how much? It is given here. 45 into 10 power 9. And B we know it is 2.55 into 10 power minus 10 whole square. So it will be 14.6 into 10 power minus 10, right, Newton, or you can write it as joule per meter. Okay guys, so this matches with option T. Okay, so these were the questions of mechanical metallurgy. Hope this will help you for your GATE preparation. Thank you all.